So what makes Redis special? Redis is an open sourced in-memory data structure store that can be used as a database, a cache, a message broker, and a streaming engine. Redis provides some of the most amazing data structures out of the box, which are hashes, list, set, sorted sets, bitmaps, hyperlog, geospatial indexes, and streams. These data structures that Redis gives us, they help us build a variety of applications like real-time chats, message buffers, gaming leaderboards, authentication session store, media streaming, real-time analytics, and whatnot. If you look at the trend of how the popularity of Redis has grown, it is an exponential curve because people love Redis because of the flexibility and, more importantly, the simplicity of it. It finds its application across plethora of data, across basically plethora of use cases, right? And that makes Redis special. But Redis, the key highlight of Redis is that every operation that you fire on Redis is atomic in nature. By atomic, what I mean is that when a particular command that you fired on Redis is executing, your other commands, let's say you have accepted 3 or 4 connections. It's not that your command execution would pause in between and some other command will be scheduled. No, when one of your command is executing, after that execution is complete, then only another command would be executed. This is the beauty of Redis. This is where it makes its stamp, its authoritative stamp, saying that, hey, I am atomic in nature. Any command you fire, you don't have to worry about concurrency at all, because every single thing that you are putting in is atomic in nature. While that is executing, there is no context switch that would happen. So for example, when you are putting a key, atomic, adding to a list, atomic, doing set union, intersection, atomic. Just imagine when you are doing set union and not having to worry about some other thread or some other parallel thing putting the value while you are doing this union. That's the best part, right? This is the power of atomicity that Redis exploits. And more importantly, incrementing the value. We know that count plus plus is not thread safe. Here, incrementing the value is atomic, which means that even if you accept requests from 10 TCP connections or from 10 clients, all of them trying to do incrementing a particular key, the final value will be 10. It will not be 11, it will not be 9 or 8 or 7. So every command that you fire on Redis is atomic in nature, which is brilliant part on the Redis. Right? Second, the data is stored in memory. This is the best part. Why? Because that's why you would see Redis being used as a cache in most of the applications. And most people unfortunately don't know that Redis can be used for other purposes as well. This is where the in-memory storage comes in very handy. But Redis also provides a configurable persistence, which means that you can configure, when you start your Redis server, you can configure it such that you can tell, hey, periodically dump the data onto the disk. So whatever the data is there in the memory, it would dump it onto the disk. Right? It would not be deleting anything from memory, but it would be dumping whatever it has periodically to the disk, so that if in case your Redis process crashes and it reboots, it does not start from scratch. It can load the last file that it dumped and it can load it and start from the point of the last checkpoint. Right? It can also provide partial persistence to write ahead logging, which means that every command that you fire, every update command that you fire will be logged in an append only file, which is an AOF file, which basically Redis calls it AOF file. It logs it everything into that, which you can use to reconstruct your Redis. Right? Or you can set up a synchronous replication to another Redis server. So this is where your write ahead log file comes in very handy. And you can also configure the persistence, saying I don't want persistence at all, just keep everything in memory. Whenever you crash, I'm okay losing all the data. Other key features that Redis provides are transactions, which means that while that one transaction is executing, nothing else would do. We'll talk about rollback in detail on how it handles that, but it does provide transactions. It provides pub/sub, which means you can have a publisher and a lot of consumers listening to the same Redis on a particular topic, When a publisher publishes, automatically all the consumers listening to that same topic receives the message. It's a push-based message that they would receive. So you can build your entire PubSub and you can use Redis as a PubSub for that. Other key feature is that there is TTL or expiration on the keys, which means you can say that I'm putting this key in Redis and after 5 minutes automatically delete that. That's an excellent feature that would help you keep your usage in check. Right? You are putting in value and without any expiry, which means it would keep it there permanently. You would have memory leaks in your system. With expiration, you can automatically say that, hey, let me put my authentication on that with an expiration of 30 minutes. After 30 minutes, authentication, like that particular key would be automatically deleted, which means that user would be automatically logged out. So for anything temporary, this is an excellent place to build. And LRU eviction. Key eviction strategy. So when your cache is full, you need to evict the key, and it has its own configurable key eviction strategy, which means that it would still be accepting the writes. It will not crash, it would accept the writes, but if the cache is full, it would be evicting the key. And that's the brilliant highlight of that you don't have to manage anything. Redis does that thing automatically on its own. Right? Now we'll talk about the programming models. So this is where we need to understand how Redis is able to handle large number of connections. We are still laying the foundation, while implementation will get much deeper understanding on how it is actually implemented. But let's talk about the concurrent programming models over here. So here, what the given state is that you have a single process, like we have MySQL Postgres process, you have a singular process. Within that process, you want to handle multiple requests concurrently. How do you do that? So there are multiple ways to achieve concurrency in a single process mode. Now, this is all about concurrent programming. There are two possible approaches. The first one is multi-threading, the most common one. So here what you can do is, whenever you get a command to execute, whenever a client connects to your database, you spin up a new thread and let that thread handle the request coming in from that client. So for example, if you have request 1 coming in that wants to do increment k, you would spin up a new thread that does increment k. If you get request 2 that does increment k, you would spin up another thread that does that same operation, increment k. So every client that is connecting to your database, you are creating new threads for every client and let that thread handle anything and everything. This leads to a problem. This leads to a problem where we have to ensure data correctness. Because what could happen is that if, let's say, the value of k is 10 and I have 2 threads. If value of k is 10 and I have 2 threads, they both executing k++, right? K++ on the same value k or the same variable k. Then what would happen is, if you do not have proper guardrails, what would happen is both the threads would read the old value of k, 10. Both of them would increment to 11 and they both would write 11 over there. So even though I have 2 threads, but when I'm doing increment twice, because 2 threads can execute on 2 different cores or even on the same core, that same problem exists, that there is a possibility where my final value can also be 11 or 12, and it is an unpredictable behavior. You never know when you would get 11 and when you would get 12. This is a classic problem of concurrency, where your count++ is not thread safe. So one way to solve this problem is to make one thread wait while other executes, which means that if I have 2 threads coming in, I'll write the code such that they would need to acquire some lock, and only one thread is allowed to acquire the lock, while the other one would be continuously waiting on that. So I initially have 2 threads coming in and they would both be waiting to acquire the lock. One of them would get it and it would move forward, while the other one continues to wait. When the one thread executes, so your k++ is your critical section. One thread would be executing k++ while the other one waits. Then this thread goes to release lock. As soon as it releases the lock, the other thread is allowed to move in and it would do k++. Because of this exclusivity, you are putting that guardrails so that you never end up with 11. You will always end up with 12. This is what you would have to do to ensure the data correctness, right? And the way you can achieve this is through mutexes and semaphores. Very common strategies to do that, right? These fall under pessimistic locking. Out of scope of this part because we are building a single threaded database. But if you are interested, deep dive into mutexes and semaphores, right? And through this, you can implement locking or basically pessimistic locking, right? Now let's talk about the more interesting part which Redis adopts. It's called IO multiplexing. So this is an apparent concurrency model, which means that you are not achieving true concurrency, you are achieving apparent concurrency. So the idea here is that with threads, it is possible that two threads will be scheduled on two different cores of your computer or of your server. So you are getting true concurrency, right? Here it's apparent concurrency. So here the idea is that anytime, like why are we even talking about this? Because IO, whenever you are doing a disk IO or a network IO, system calls happen in the background. Happen in the background as in, let's say you want to read from a socket. You have to fire the read system call. Read system call, it's same in all operating system. Every single operating system exposes a set of system calls that you have to use to do IO operations, be it disk IO, network IO or anything. Right. So now when you would want to read something from the socket, you would initiate a read system call. And this read system call is blocking in nature, which means that if I have two devices or two servers connected over a TCP connection, and if one of them fires a read, let's say my first server fired the read system call that it wants to read from the socket, right? This is a blocking call, which means that the call would not proceed until my connected client sends something over the network. This is painful. This is extremely painful because with IO, if you are waiting on something, you are not making any progress and you are just blocked. So can we do better over there? That's the idea behind IO multiplexing. So can we multiplex when we are waiting for IO to complete? So here, hence we cannot just invoke read request on a socket unless we know that there will be someone sending the data to us. For example, if you don't know if the other party is going to send you the data, and if you fire a read system call, then you are just blocked there for a particular timeout. You are just blocked unnecessarily. So that waste of CPU, memory and whatnot, right? So this is what makes us use IO multiplexing in such cases. So to handle this, a popular approach that we just discussed is multi-threading, where while one thread is waiting, we can have other threads getting scheduled on the CPU to get things done, right? That is where multi-threading based approaches comes in handy. That is one way to solve that problem, that each thread would fire its own read call while it is waiting for the IO to complete. Other thread who are ready to execute can be scheduled on the CPU, right? And this is the core idea behind achieving true concurrency using multi-threaded system. That's why all multi-threaded web servers are implemented exactly like this. Whenever a new connection is formed, it spins up a new thread, and that thread does take care of the IO that needs to be done. This way, if one thread is blocked, other thread can be scheduled because it goes in the block state. Operating system schedules another thread which is ready to be executed, right? But when we do this, as we just saw, we have to use mutexes and semaphores to protect our critical section, right? And which makes things slow because my two threads. Now, why is it making things slow? Because what we saw was when you have two threads, you applied mutexes or semaphores so that you can protect your critical section. Now, these threads were not waiting for any IO. These threads were ready to be executing. They were not waiting for IO. They just wanted to do count plus plus or k plus plus. They were all ready and roaring to be executed. But what you did is you added this mutex, this pessimistic blocking, which allows only one to move forward. This is the pain point. So a thread that is ready to be executed or can move forward, you are unnecessarily blocking it because you want to ensure correctness of the data. And that is also important, right? So can we do something? An idea over here is, can something notify us when there is some movement in the thread, or sorry, in the IO. So let's say you have a TCP connection open, ping me when there is something happening there. Then only I will fire a read request. That's a very simple analogy, right? But this is the world of IO multiplexing. So the core idea here is that we use IO monitoring calls to monitor the socket and fire read request on the one that has some data. This is the core idea, that we not fire read request until we are 100% sure that there is some data to be read. And this is the world of IO multiplexing, right? We'll go in detail. So for example, here and this is what your event loop also looks like. This is how Redis also operates. So any single threaded database or process that claims to be supporting large number of concurrent IOs, this is what they do behind the scene. This is how the execution looks like. Everything is still a single thread. There is nothing changed over there. It's not multi-threading. Event loop is not a separate process. It's not a separate thread either. Everything is running in this one thread only, right? And the idea is that, let's say you get a lot of TCP requests at the moment. Your server just started, you got a lot of TCP requests at the moment. So what did you do? You accept lot of TCP connections using system call. We'll talk about implementation in the next video, but just understand or just absorb the essence of the idea, right? So it'll accept large number of TCP connections over here, right? And you read from one of the sockets. So let's say you accepted connection from 4, then you read from one. The one that you read from, like you got to know that one of them has data that you can read. You read from that one socket and then you execute because you read a command. Let's say we are building Redis, you read a command and you are executing that command, right? And let's say it took you 3 time units to execute it. And then you again checked, is there any other socket which has some data for me to use, or it has some data for me, and you found there is one more socket, and you read the data that came in, which is the command, and then you executed it. And then you check, are there any socket that has data? No. You check, are there any incoming TCP connections? Yes, there are 2. So you accepted them as well. And then you check, are there any sockets that I can read from? You found one. So then you started executing, and so on and so forth. Here, you can very clearly see how we are accepting multiple TCP connections, picking one that has the data immediately that it has sent you. Using that incoming data, you are executing the command that has been provided and then moving to the next, right? This is the idea of a single threaded event loop. This is what event loop does. Any IO operation, whenever there is some data, something, then only you are taking these actions, and system calls tell you when there is data available for that. You don't have to do anything. System calls are there to use. You just have to use that corresponding system call. Right? And this makes Redis extra special. This is how your Redis evaluation actually happens, right? So just to summarize, event loop is not a separate process. It is neither a separate thread. Everything just happens in this one single thread. Accepting the connection, reading from the socket, executing the commands, everything happens on this one single thread. Now I will say, Arey, but then how is it fast? How is it Redis being able to give us such high throughput? The idea is pretty simple. What Redis beautifully exploits is the fact that network IO is slow, because someone sending you the data over the network is a very slow process. You reading the data is a very slow process. In most cases, when you are doing an IO heavy server, let's say your Redis is an IO heavy use case. Anything that you build, your Redis is a classic example for that. Let's say you're building a web server that is also IO heavy. You get a request and then you process it, right? So in those cases, you're waiting for a very long time to receive commands or request. But in case of Redis, your operations that you do, increment, adding to the list, they are all memory operations because Redis is an in-memory data store. And because your operations, when you receive a command, the operation that you have to do, they are all in-memory operations. They're extremely fast. It's just about adding a new value in the array or updating a value in the array or adding a node in the tree, something like that. It's extremely fast. So upon receiving the commands from the client, Redis can very quickly execute them. So the time it takes for Redis to execute the incoming command, it's extremely fast. This is what Redis beautifully exploits. So this is why Redis made this conscious decision of keeping itself single-threaded so that you don't need the complexities of mutexes, semaphores, and unnecessarily your threads getting blocked. The threads that are ready to be executed, they are getting blocked unnecessarily. That's why no complexity of mutex, semaphores, data correctness and whatnot. Everything is single-threaded. And by doing IO multiplexing, it is still accepting large number of TCP connections concurrently, evaluating them one by one, given that execution after receiving the command is just an in-memory operation. It would happen extremely fast. That's why Redis is able to support large number of TCP connections while being extremely fast at executing them, because every operation is just an in-memory operation. And this is what makes Redis extra special. So that's it for this video. I hope you had fun understanding what makes Redis extra special. In the next video, we'll be building our own TCP server in Golang and laying the foundation of our own Redis implementation. Right? Thank you for watching and I'll see you in the next one.